Okay, welcome to section 3.9, derivatives of exponential and logarithmic functions. Let's get started. Okay, the very first question is to find dy dx if y is equal to e to the x power. Okay, so actually we can start this off by using our limit, our definition of a derivative, the derivative of e to the x. So it will be e to the x plus h minus e to the x all over h, and then the limit as h goes to 0. Okay, we can take our e to the x plus h and write it as e to the x times e to the h. We can factor out an e to the x. We're taking the limit as h goes to 0, so the actual e to the x factor here is considered constant under any changes in h, so we can pull that out to the front. And this is one of our special limits. The limit is 1. So we have e to the x times 1, which is e to the x. Okay, now this is remarkable. The derivative of e to the x is itself. Very interesting. Okay, not only is it interesting, it's also very useful, and it shows up quite a bit for the rest of the year. Okay, so the derivative of e to the x with respect to x is e to the x. Let's write down the chain rule for that. The derivative of e to the u with respect to x is e to the u times du dx. Or if we want to go with this notation, we could say the derivative of e to the u, and the prime implies that the derivative is being taken with respect to x, is e to the u prime. This is a nice way to write things. Just don't confuse the hash marks, the prime marks for power 1. Okay, for our first official example, we're going to go ahead and find the derivative of e to the x squared. Okay, so in this case you can see that we're basically doing a chain rule here. E to the x has derivative e to the x, so e to the x squared starts off by simply being, derivative is just simply e to the x squared. Now we need to multiply by the derivative of our inner function, which is x squared. The answer is 2x. The answer is 2x e to the x squared. Okay, our second example here is x times e to the negative x squared. Okay, so it looks like a product rule. It's made up of two functions, x and e to the negative x squared. Okay, so this will be kind of like our two functions, the u and the v from the product rule. Okay, so the derivative will be made up of 4 parts. Okay, the first function's derivative times the second function plus the first function times the second function's derivative. Okay, so here we have a 1, and then we have e to the minus x squared, and then we have an x, and this part we did back in example 1, except it was a negative. So basically it looks like e to the something, So we start off by writing e to that same thing, and then we multiply by the derivative of that something. So it's negative 2x. And if we take out the e to the x, the negative x squared on this, we have 1 minus 2x squared. Okay, the next topic would be to talk about bases other than e. If the derivative of e to the x is itself, what would be the derivative of something else to the x? Okay, well, we can try to do a rewrite. Sometimes it's important to rewrite a problem before we actually attempt it. So we're going to go and write this as e to the ln a to the x. Now, e to the ln of something is just that something. So actually this is y equals a to the x. These cancel. So I'm putting them in. You'll see why. Okay, in order to do this, I'm going to in order to do this, I'm going to be able to I'm going to need to use the e to the x rule. So this now looks like e to the something. See, so that's the trick. All right, so let's go ahead and find the derivative of a to the x, which we've since written as e to the ln of a to the x. Okay, well, it looks like e to the something, so we start off by just simply writing that same something. So remember, the derivative of e to the something is just e to that something times the derivative of that something. Okay, so the derivative of that something we have to figure out. So we need to find d dx of ln a to the x. That's the something that's up here in the e. Okay, fortunately there's a different way to write ln of a to the x, and that is using x ln a. Okay, and the ln a is a constant. Okay, so we have e to the ln a to the x times ln a times dx dx, which is just 1. Okay, so this ends up being e to the ln a to the x times ln a times 1, and now we can undo what we did earlier, or remove those, not the entire thing, but just the e to the ln. In other words, this is a to the x times ln a. Okay, so this is the derivative of a to the x. And the chain rule is d dx of a to the something equals a to that something times ln a times, and then the derivative of that something. So there's the chain rule. Or if you want to write it as a to the u differentiated with respect to x is equal to a to the u ln a u prime. Okay, let me just show you how easy this really is to use. Okay, so let's take a look at an example. Okay, the example I've picked is similar to the last one, one of the last ones we did, where we had e to the x squared. And remember that the derivative of e to the x squared was, let's go back a page, simply e to the x squared times its times the derivative of that x squared. So let's go to our problem at hand. Okay, so we're going to be finding the derivative of 5 to the x squared. So this looks like the derivative of 5 to some power. So it's just going to be 5 to that same thing times. And then we have an ln 5 that goes with the fact that this is not an e base. And then times, and then we have the 2x, which is the power for the, or the derivative of the exponent. Okay, and carrying on with that same thought, if we were to do this problem here, we start with the derivative of 3 to the something, which gives us that same expression, times an ln 3, because it's not a base e, times, and then the derivative of a cotangent, which is a negative cotangent x, times cosecant x. Okay, our next example is an example of a product rule problem. Okay, so we'll start off with writing out the question. So we have sine x times 2 to the power, and this is all in the exponent here, 3 to the x plus 4x squared. So watch your handwriting size there. Okay, so we have first function, the derivative of that, times the second function, as is, plus the first function times the derivative of the second function. And I haven't done any calculus yet, I was just getting it that kind of all set up. You know, I like to set those up ahead of time. Okay, so now let's take a look at what we've got. So our first term is cosine x, that's the derivative of sine, and then we have this ridiculous expression. Okay, secondly, we have a sine, and now the derivative of this part. Obviously this is the tricky thing to work on, so first thing we notice is that it is 2 to the something. Okay, 2 to the something is, the derivative for that is just going to be 2 to the something. So we're going to copy that exact expression, times, and then ln 2, and then times the derivative of that something. Okay? Alright, so we'll start off with red, because I've underlined the 2 to the something in red. So it's 2 to the something times ln 2. Okay, now we're supposed to multiply by the derivative of that something. That something is this part up here. So, to do the derivative of that, we will now multiply by the derivative of what's up there. Okay, the derivative of what's up there is going to be, since it's 3 to the x, we have 3 to the x ln 3 plus, and then we have a 4x squared, so the derivative of that is 8x. Alright, and there you have it. And we do have a common term that we could technically take out, and that's this blue term right here. Shows up in both of these. This is actually quite common for us to be able to factor something out. Okay, so we'll do that. We take out the 2 to the 3 to the x plus 4x squared. We have a cosine x plus a sine x times an ln 2 times, and then we have a 3 to the x ln 3 plus 8x. I don't know why we took that out. It didn't really make it look that much greater, but it is interesting that we can't take it out. And that was example 5. Sorry about that little skip there. Okay, let's go on to our next topic. For our next example, we'll do a word problem that involves finding the derivative of an exponential. This is pretty common to see a formula about the spread of something. There are models for these. This one is the spread of a flu at a certain school. Okay, so go and write down the question. Alright, the first thing we'll be asking here is to estimate the number of students infected initially. Okay, so let's put that in. Estimate the initial number of students infected. Okay, so this would just basically be finding p of 0. That's what this is. So we're trying to find when time was 0, that's the initial starting amount. We have 200 over 1 plus e to the 5 minus 0, or you could say just 200 over 1 plus e to the 5th. Okay, well it turns out that this is about 1.339. Alright, so let's make this approximately for the test. Okay, and so we understand this to mean one student so far has been fully infected. Looks like another one's on its way. So 0.3 of a person is infected. We'll just put one student. Okay, so the disease started with one student. Okay, the next question we want to ask is how fast is the flu spreading after 4 days? Okay, so this is very important to understand this. When we say after 4 days, what we really mean is on the 4th day. Or you could say at t equals 4. So it doesn't say what was the average rate of change of the flu's spreading during the first 4 days or over the first 4 day interval. It doesn't say anything about average. We're talking about instantaneous. Okay? So this is an instantaneous rate of change. Okay? And they're giving us an a value. So we're obviously finding a derivative here. Okay, so we're going to be doing p prime of 4. Okay, so to do that, we're going to need to take the derivative of p of t and plug in the time 4. Okay, you're welcome to do this on your calculator, but I thought I'd at least show you how I would set it up by hand here. The first thing I would probably do is go back to my original function and move this here. Okay, the original function was not written in a very friendly form. It was p of t equals, and then it was 200 over 1 plus e to the 5 minus t. I would rather write that as 200 times 1 plus 1 plus e to the 5 minus t to the negative 1. This allows me to apply the chain rule directly to it. Okay, so we'll start off by treating it as 200 times something. So we can just leave the 200 there. Okay, in the front. And it's 200 times something to the minus 1. So we're bringing down the minus 1 as a first thought. Okay, so let's bring down the minus 1, and we'll have that same something to the negative 2 power. Okay, that object that was raised to the power is our inside function, so that needs to be differentiated. The derivative of 1 is 0, plus, and then we have e to the something. So we know now that means we're going to be doing the derivative as e to the something, and then times the derivative of that something. So the derivative of that something is this blue part right here. The derivative of 5 minus t is simply negative 1. I think I'll just put the negative 1 right there. Okay, I highly encourage you to go back and just rewind that real quick so you can process what I just did. I color-coded it for you, but you should probably watch that again. Okay, hopefully you understood that. You should work it out on your own if you don't have it. Okay, and then this is to be evaluated at t equals 4. Alright, so let's just plug in the time. Okay, so we will enter in negative 200 times 1 plus e to the 5 minus 4. So that's just e to the minus 2. And then this is just negative e to the first. Both of these 5 minus t's are simply 1. 5 minus 4 is 1. Okay? Alright. If you enter this into your calculator, you end up getting about 39.32 something or other, which we'll have to treat as about 39 people per day. Remember the units here. People infected, that's the P. Per day, that's the time. Okay, now the last question to ask for this problem is the following. When will the flu spread at its maximum rate? Okay, now to answer this question, we need to understand that maximum rate really is the derivative. We will need to find the derivative of the derivative, because a maximum rate implies that the rate function, the derivative, has a horizontal tangent. Okay, so we're going to need to set p double prime of t equal to 0. Okay, now to get the second derivative, we would need to go back to our previous result and take the derivative again. That's a kind of a tedious task. There was our derivative, remember? So we'd have to take the derivative of that again, and then set it equal to 0 and solve. Okay, the other option is to look at maximum point on the p prime of t graph. That's another possibility. Okay, so what I'm going to actually do is use my calculator for this. So I'm going to pull up my calculator. Okay, and you can already see that I've entered in the 200 over parentheses 1 plus e to the parentheses 5 minus x, which is our population function for number of infected people after time t. Okay, for the p prime of t, I'm going to enter in math 8 variables y1, comma x, and this will give me the function, the values for the rates of change. We could have done this, by the way, to get part B. Okay, now to get the maximum value, why don't we look now? We'll also probably put in the second derivative, but let's take a quick look at our table. So I'm doing a table set. I'm starting on the 0th day and going by 1 day intervals. Let's look at our table. Okay, so what you see here is only y2. Let me go back to my editor. You can see I've turned off y1. Actually, let's turn that back on too. So let's look at both of them. Oops. I don't really care about the graph. Let's go to the table. There we go. Okay, so you can see here y1 means the first day one person was sick and was growing at the rate of about 1 person per day. Second day, 3 people were sick, growing at about 3 per day. And then 9 people were sick, growing at 9 per day. And then 23 people were sick, growing at about 20 people per day. So the first column, y1, is the number of people infected. The second column is the rate at which people are getting infected at that time. Okay, so for example, on the 4th day, there are 53 people sick, and the rate is 39. This number 39 is the number we got for part B over the 4th day. Okay, but then the question says, when does the rate reach a maximum? We can kind of see it right here. It goes 39 people per day, 50 people per day, 39 people per day. So it just maxed out at 50 people per day on the 5th day. Okay, so turns out that the maximum rate, y2, is 50 people per day, and that was on the 5th day. So that's the answer to the question. Okay, so we'll write it down. On day 5, the rate reached a maximum of 50 people infected per day. Okay. And if you would like to actually know that rate, you would write 50 people infected per day. Okay, so let's put that question here too. That's an important question too. What was that rate? Okay. Alright, and the book asks the same question. I'm just curious about that 5th day. I want to see the second derivative real quick. So I'm going to go back and go to y equals, and under y3, I'm going to enter in math 8, y2, go down one to y2 there, comma, x, and I'm going to go ahead and turn off y1. I'm done looking at the people being sick. Look at the growth rates and the rate of growth for the growth rate. Oops, I want the table. Okay, so y2 is the growth rate, and y3 is the rate of the growth rate. So we're looking for 0 in the third column. Well, there it is, right there. 7.5 times 10 to the minus 7th is close enough to 0. You can see in this column that the rate went 1, 3, 9, 20, 39, 50, 39, and then it just goes down from there. In fact, it seems symmetric. Your growth rates were increasing and then decreasing. Right here on the 5th day, the growth rate is 0, which means the rate is at its peak. And this is similar to looking at an acceleration idea here. Okay? Alright, so I'm pretty convinced with that 0 there and that 50 being larger than the 239s, I think it was the 5th day.